Flow measuring device. In the flow measuring device, we are going to study different types of flow meters. Basically, there are two types of flow meters, variable area meter and variable head meter. As the name suggests, variable area meters are those meters, or I can say are those flow meters in which area of the flow varies. Variable area, that means in variable area meter, the area of the flow varies and the pressure drop remains constant. While in variable area meter, head meter, opposite to variable area meter, variable head, that means in variable head meter, the pressure head is going to vary and area remains constant. Clear? In variable area meter, area is vary and pressure head remains constant. While in variable head meter, pressure head varies and area remains constant. In variable area meter, we will see rotameter. The type of variable area meter is rotameter, while the type of head meter covers orifice meter, Venturimeter and pitot tube. So basically in flow meters, there are two types, variable area meter and variable head meter. And in variable area meter, there is rotameter, and in variable head meter, there are orifice meter, Venturimeter and pitot tube. So in this chapter of measuring flowing fluid, we are going to study all these type of flow meters in detail. So let us start with first variable head meter. In variable head meter, first is Venturimeter. Basically, Venturimeter consists of three sections. Venturimeter, which comes under variable head meter, consists of three sections: converging cone, throat diameter and diverging cone. Basically, these sections are divided based on the area. The area is fixed, as this flow meter comes under which category? Variable head meter. Converging cone is nothing but the area of decreasing section. The area of flow is decreasing. Throat diameter is nothing but the constant cross section or constant area, and the diverging cone is the area of decreasing section. See the figure. In figure you can see this. See, this first section starting from here to this here, you can see this taper section, that means the area is decreasing. That is known as converging cone, the area of decreasing section. This middle part, this middle part is throat. It is known as throat, that is of constant cross section. And this last part, see, this last part is where area is increasing, that is known as diverging cone. So this whole Venturimeter, see, this whole Venturimeter is divided into three sections: converging section, throat section and diverging section. Now how we can measure the flow? An increasing in flow velocity at the throat results in decrease in pressure at the throat. Imagine that the flow rate is starting from here. See the arrow, the flow is starting from here. It passes from first from converging, then from throat and then from diverging. So what will happen? The velocity of flow increasing at the throat, and it results in decrease in the pressure at the throat. Due to this, the pressure difference is developed between the inlet section and the throat section. Understand? There is a development of pressure difference at inlet section and throat. And due to this pressure difference, we have to measure this pressure difference with the help of manometer. So here we installed a manometer. And with the help of that manometer, we are going to measure this pressure difference, which is created between inlet section and throat section. So due to this pressure difference is developed between inlet section and throat, which is measured with the help of manometer. So from this difference in or varying in velocity, we measure the pressure difference, and from that we can easily measure the flow rate. In next step we will see how to measure the flow rate from that pressure difference. So by this way we can measure the flow rate with the help of Venturimeter, which comes under the category of variable head meter, and this is the figure of Venturimeter. Now let us discuss about the advantages and disadvantages of Venturimeter. The advantages of Venturimeter includes it creates moderately low pressure loss. In Venturimeter there is low pressure loss, there are no moving parts in Venturimeter. It provides high accuracy and less power loss. So these are the advantages of Venturimeter. Let us see the disadvantages, which includes that Venturimeter is expensive and bulky. The cost of the Venturimeter is high and it is bulky, so it requires considerable high space for installation. It occupies considerably high space because it is bulky in construction. Another disadvantage is that it is not suitable for flow measurement of highly viscous slurry. If we have to measure the flow rate of high viscous slurry, then we cannot go for Venturimeter. Fine. So these are the advantages and disadvantages of Venturimeter. Now let us discuss the flow equation of Venturimeter. Now what is this flow equation? Basically the flow equation is used to calculate the flow rate of fluid using Venturimeter. So in this topic, at the end we have to achieve an equation which is used to calculate the flow rate of the fluid. So let us see, this is the Venturimeter. As I have already told you, in this Venturimeter we have to attach the U-tube manometer for measurement of pressure difference. So let us consider here there is point number 1 at the inlet section, and at the throat we consider point number 2. Now there is pressure difference between point 1 and point 2. And that's why we have attached U-tube manometer between point 1 and 2. As there is a pressure difference between point 1 and 2, this is my point 1 at inlet section and this is my point 2 at throat. Now let us consider the pressure is P1 at point 1, velocity is U1 and Z1 is the height. Similarly, at point 2, pressure is P1, velocity is U2 and height is Z2. So now, if I apply Bernoulli's equation between point 1 and 2, then how can I write that equation? See here. Now we all know about the Bernoulli's equation. See, P1 by rho plus alpha 1 U1 square by 2 plus GZ1 is equal to P2 by rho alpha 2 U2 square by 2 plus GZ2. So this is the Bernoulli's equation I have written between point 1 and 2. Point 1 is at inlet section and point 2 is at throat section. Now in this, as the Venturimeter is installed in horizontal level, what will happen? Z1 is equal to Z2 as Venturi is connected in horizontal pipeline. So Z1 is equal to Z2. So now my Bernoulli's equation is reduced to this term. Z1 and Z2 is cancelled out because Z1 is equal to Z2. So now I can write this equation as P1 by rho plus alpha 1 U1 square by 2 is equal to P2 by rho plus alpha 2 U2 square by 2. I have named this equation as my equation number 1. Now here I am using equation of continuity. We have already studied this equation of continuity and Bernoulli's equation. So according to equation of continuity, m dot is equals to rho u1 a1 equals to rho u2 at. u1 a1 is the velocity and cross section area at inlet section, and u2 at is the velocity at throat and cross section area of the throat, which I have mentioned as at. Cross section area I can write as pi by 4 d square. So see, a1 is equals to pi by 4 d1 square, at is equals to pi by 4 dt square. Now here, rho u1 a1 equals to rho u2 at, I can write this as u1, rho is cancelled out as the fluid is same, so density of the fluid is same. So u1 pi by 4 d square is equal to u2 pi by 4 dt square I can write. Now here I am introducing a term beta, which is a diameter ratio dt by d. So dt by d is equals to beta, which is diameter ratio. Diameter of the throat divided by diameter of the inlet section. So dt by d is equals to beta, which is called as diameter ratio. So in place of u1 I can write dt by d whole square into u2. So dt by d is what? Beta. So u1 is equals to beta square u2, I can write that. Now I can simplify this equation. Now put this u1 value in this equation number 1. u1 is beta square u2. Putting that in equation number 1, substituting this in equation number 1 and simplifying the equation, here I am taking alpha 2 by alpha 1 is equals to 1. We reach to the equation. Now, what I have to do? Put this value in equation number 1. Simplify that equation and taking alpha 2 by alpha 1 ratio is equals to 1. After doing this exercise, you will reach to a equation u2 is equals to 2 p1 minus p2 upon rho into 1 upon alpha 1, 1 minus beta raised to 4, and whole this equation raised to 1 by 2. That means this equation is in under root. When you simplify this equation, you will reach to this form. Now I have the equation for u2. u2 is the velocity at throat section. If I have velocity, then I can calculate the volumetric flow rate Q. See, in this whole derivation, we have assumed that there is no friction. When you reach to this u2 equation, here we have taken assumption that there is no friction generated. But in actual practice, there must be friction exist. So we have to consider a correction factor for friction exist. So I have entered here a correction factor which is known as coefficient of Venturimeter, and I have used term CV. CV is coefficient of Venturimeter. So in this above equation, I have introduced a coefficient of Venturimeter CV. So U2 is equals to CV under root of 2p1 minus p2 upon 1 minus beta raised to 4 into rho. Fine. So this is the final equation of velocity at throat U2, introducing the correction factor. Now, what is our final aim? Our final aim is to calculate flow rate. Volumetric flow rate Q is equals to velocity into area. If I have the value of velocity and area, I can easily calculate the flow rate. So now volumetric flow rate capital Q is equal to U2 into AT. U2 is the velocity at throat and AT is the cross section area of the throat. So now put value of U2 and AT here in this equation of Q. By putting the value of U2 and AT and simplifying the equation, you will reach to a form capital Q is equal to CVAT under root 1 minus beta raised to 4 into under root of 2 P1 minus P2 upon rho. So this is my final equation to calculate volumetric flow rate through Venturimeter. Additional to this, we are generally use U-tube manometer. Now we have the equation of calculating pressure difference by using U-tube manometer. Remember that P1 minus P2 is equal to delta H rho m minus rho into G. Now put this equation here. In P1 minus P2 is equals to delta H rho m minus rho into G. Where it comes from? It comes from the U-tube manometer equation. As U-tube manometer is generally used for measurement of pressure difference, we can write these above equation as Q is equal to CVAT under root 1 minus beta raised to 4 into bracket under root 2 delta H rho m minus rho into G upon rho. Now, what we have do? Putting P1 minus P2 is equal to delta H rho m minus rho into G. It comes from the equation of U-tube manometer. So this is my final equation, or I can say this is my flow equation for Venturimeter. This equation we are going to use when we will solve the examples of Venturimeter. So in today's session we have covered the Venturimeter in detail along with its advantages, disadvantages and flow equation. I hope this is clear to all. Thank you very much.